Okay, so last time we were here, we did transforming with logarithms. We did how to transform a power model, right? The power model meaning that it looked like this. Okay, and how do we achieve this? We took the natural log of both sides, right? Natural log of y is equal to natural log of a plus natural log of x.
I know it's just normal log.
Okay, we're we doing normal logs?
Yeah. And
Not that it matters, it's the same, right?
what isn't it like instead you raise it to like by 10?
Yeah, same thing, right? But you get the same effect.
Okay.
Okay, so the b came over, correct? And then right like that, right? And so we were basically taking the common log of not only the response variable, but also the x value, right? Okay, so we're taking the log of both sides, okay? So the explanatory variable and the response variable. Okay? So this time we're going to do an exponential model. An exponential model is different than this, correct? Because this is the power model, right? So let's just so you don't misunderstand it. This is the power model. And now we're going to do the exponential model. The exponential model is called exponential because the exponent in the exponent is where the x is. Okay? All right, like 2 times e to the x or 3 times e to the x or something like that, right? So when we transform this, when we transform this, we're going to do the same thing. We're going to take the log of y, which becomes a log of a plus log b to the x, right? X jumps forward. So what's the difference between these two?
X is like the code.
So here you have the log of x times b, where you have the log of b times x. So in this transformation, you're only taking the log of the response variable. You're leaving the explanatory variable the same. So you're not transferring that side. You're only transferring one side. Okay? That's the biggest difference. Okay? Okay, so let's go over there. Let's look at the example on page 804. Moore's law. Anybody remember Moore's law? Anybody, especially if you've read Tipping Point? Was it Tipping Point or Outlier? Outlier, was it Outlier? Anyway, so okay, Moore's law says that Gordon Moore, one of the founders of Intel, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. So what does that mean? Why is having more transistors on a chip better than having less?
It's faster.
So the more transistors you have, the more computations you can do, obviously, right? Okay, the more computing power, right? Well, why don't we just dump more and more and more transistors in? What's the problem there? Does anybody know? No.
Money.
Money is one. Good job. What else? There's really, I mean, technologically, there's the heat issue, the issue of heat, okay? Because the chip overheats so quickly when you have so many transistors in there, okay? So it's always been, that was always one of the things, and that was one of the things that why people were going to optical chips, right? Where you didn't need that. You didn't need transistors. It was all light, less heat. Okay. All right. Anyway, so if you go there, it says that every 18 months, you're going to double every 18 months. Okay. So this is the Moore's law, one way. So basically, that kind of sets the lifetime or the life expectancy of a computer. So every 18 months, the chip speed, the computing power doubles. So therefore your computer becomes more and more obsolete in a year and a half. Every year and a half, you have to go out and buy a new one. Okay? So that's what that is. Okay? And here are the data, dates, transistors, blah, blah, blah. Okay, so that's what they're showing. So if I graph through the scatter plot, I get the one on the top, on the bottom there, right? Is scatter plot between the transistors in billions and the years since 1970. Okay. So if I take the natural, it looks like okay, now in this one they took the natural log. If I took the natural log of the response variable there, which is the transistors, you achieve something that looks pretty darn linear there. Can you see that? Can you see how once you make the transition, how that changes? Okay. So based on the graph, explain why it would be reasonable to use an exponential model. Okay, so the reason why I can say that that is an exponential model and not a power model is what? How can I tell the difference?
Because you only did log to the one.
On one side, right? Because I only did it on one side, and the explanatory variable remained the same. If it was a power model, I would have taken the log of both sides to achieve the linearity. Okay? All right. And so that's there, so that's good. Let's look at B. Here is some computer output from a linear regression analysis of the transformed data. Give the equation of the regression line. Okay, so the regression line is what? So it was a natural log, right? Natural log of number of transistors, right? So you have the natural log of transistors. I'm just going to write transistors. Okay, and that the expected value of that is going to be equal to what's my constant there? 7.22 plus 0.354 times X, which is years since 70, right, or something like that, right? So this here would be what? What is that up from here? Which one is that? Nope.
Okay.
It would be log of B, right? Right? Because X is this guy right here, right? Okay, we good? Okay, so that's how you would write that. C, use your, where it says, use your model from part B to predict the number of transistors in 2020, which means that this guy here is going to be equal to what? 50. So we'll put 50 in here and just crunch it out, and you're going to get what?
Big number.
Big number, 24.93. 24.93. So this would not be your final answer. What you're trying to find is the number of transistors, right? What you found is the natural log of that number. So the actual answer is going to be this guy, right? Okay, we good there? Right. Okay, so that's that. Flip the page. So what does this all mean? So the real question is that, okay, so we talked about how to transform. We talked about the power model. We talked about the exponential model. Initially, we talked about the rockfish, and we did like the cube root of one side, or we cubed one of the other sides, or something like that, right? So we finagled it that way too. Okay. So the real question is, which one am I going to use, right? When I come to a situation where I get to pick and choose how I'm going to transform the value of the variables, which one am I going to choose, right? And I think that's on page 807. 807, choosing a model. What's a planet anyway? Let's have our professional reader read this. Braden, please.
On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They first observed this object almost 2 years earlier using a telescope at Caltech's Lunar Observatory in California. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 6.3 billion miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are data on the distance from the Sun and period of revolution of those planets, along with the scatter plot. Note that distance is measured in astronomical units, AU, the number of Earth distances the object is from the Sun. There appears to be a strong curved relationship between distance from the Sun and period of revolution.
Okay. The following graphs show the results. Okay, so here we go. So, okay, first of all, we do not have 9 planets, right? We only have 8. Pluto is not a planet. I don't know if you guys remember this. It's not a planet. Whatever. Anyway, so there was like a movement to say, "Oh well, Pluto is a planet." So anyway, so this. Does anybody remember this?
I remember it's like 3rd grade.
Yeah. What do they actually call this? What do they end up having? What do we actually say? Is this our new 9th planet? Didn't they actually conclude that it was more of a comet rather than a planet type of thing? Because it did not observe the same orbital laws that it should have, I think. So whatever. Not a big astronomy guy. So you did the scatter plot and it shows you there the explanatory variable is the distance, and then we have the period of revolution. Okay, and it shows somewhat of showed a strong curved relationship. Okay, so we have 2 choices here. So how would you go about doing this? What would your methodology be? If you are thinking it's either a power or an exponential, which one would you rather use?
The power one.
Okay, why would you do the power one first?
Oh, well, the graph just looks straight.
Oh, okay, the graph looks straight. Okay, all right, okay, no. So, I mean, I would try the exponential model first, and the only reason being is because in order to do that, I would have to take the log of the response variable, correct? And I would leave the exponential value variable, right? So I did half the work that I would have had to do if I wanted to see if it was the exponential. I mean, if it was the other one, right? So if I try the exponential first, if it doesn't work, then I'll try the power, right? Because okay, then I'll just have to take the natural log of the other one, right? So you see what I'm saying? More work, less work, do that first and then do the other one next. Okay? All right, so based upon our result, the one on the left would be our power or was it power or exponential? Question?
On the left.
Yeah.
Why are you taking the natural log and not just the log?
Not just a log, it's exactly the same thing, doesn't really matter.
Okay.
Doesn't really matter as far as transforming. Okay, what was that question? What was the answer? The left one was what?
The power one.
Is left one the power?
Oh, that's the exponential.
Power, yeah, left one is the exponential, right? Because only the response variable has been transformed, right? Now the one on the right, you have the natural log of both sides, and that was the power, right? If you look at here, obviously the power is much more linear than the exponential. So our choice is, okay, well, that's what we're gonna do, right? So we're gonna use the power model, okay? Flip the page, go to B. Here's a computer output from their linear regression. Give the equation. So there's linear, it says a natural log of both sides. So it's the natural log of the distance, the predicted value of that. The constant was 0.00025 plus 1.499. And the natural log of the, wait a minute, this is the distance, isn't it?
Yeah.
This is the distance and this guy is the period, correct?
Why do they put a hat over it?
Because it's a predicted value,
Oh,
p hat, right? Because we're predicting that
Oh,
value,
yeah,
right?
that's right.
Right. Good question though. Okay, so that's what it's going to look like. C, use your model from part B to predict when the distance is 68.05. So we would just go ahead and go like this and go 68.05, crunch this through. If you crunch that through, you're going to get 6.33. So the natural log of your predicted period is that. So your period that you're going to predict, the predicted period is going to be equal to e to the 6.33. If you had used the common log, you would put 10 here instead of e, correct? Okay. So everybody go ahead. Where are we at? Here's what so that's number D. There's a residual plot there. If you look at that plot, what do you see?
It's a curve pattern.
The curve pattern. So alarm bells should be kind of going off here, right? This is not what you want to see normally, right? Because once you did the linearization, you want some randomness there, right? That's what you're really looking for. Okay. Here's the original and the above. Do you expect your prediction in part C to be too large, too small, or about right? Aha. So natural log of 68.05 is 6.3 something, right? 6.3 something, because the constant, the B naught, is really negligible there, 0.00025, right? Doesn't really count. So in other words, your natural log is going to be 6. So look at that original plot. What do you think the residual is going to be, positive or negative? Why? What? Because if you look right now, you're starting from -1, right? -1 to 0 all the way up to 4, and it looks like that, right? And we want to know, what do you predict at 6? So you're guessing it's going to be positive, don't you? Right?
Doesn't there like being a shape in the residual plot mean that we shouldn't be using it?
Okay, this is true. Okay, we discussed that, right? Okay. So I think the book actually justifies this, and it says that even though there is a curve, it's fairly small.
So what's the point for looking?
Okay, so let's go back to this. We're almost done here. So the residual is positive, which means that the predicted is going to be larger than the actual, or the other way around.
It's less than the actual.
The residual is AP, right? So it's actual minus predicted, right?
That's bigger.
So your actual is going to be actually larger than what you had predicted. Right? You remember
I
that?
don't know.
Okay, so all right. So we're good. We're done with that. Everybody raise your hand. Everybody raise your hand outside there in internet land. Raise your hand. Pat yourself on the back. You are done. We are done. We are done with the book.
Can
Okay?
you bring us?
Don't give me that one.
I can't.
I
It's
know.
against the school's policy, unfortunately. Okay, so.
I mean, you could just like let us not do the project. I mean, we'll accept that too. Can this be